Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Today, our speaker is in Buffalo, New York, very close to Ontario. And he will tell us about the symmetries, or actually the lack of symmetries in quantum graphs. ALEXANDRU, CHIRVASITU. It's all yours. Please take it away.
Thank you very much for that. Thank you for the invitation. Thank you for coming. Um, as Piotr just said, this is about quantum symmetries of quantum graphs. And specifically, how there are, generally speaking, not too many of them. That's going to be the moral of the story here. Not that many generically.
Okay.
Of course, there are some, right? We all do that. And I expect most of this will be, at the risk of it being a little boring to you, since I have so long, I'm going to spend quite a bit. I'm going to take my time on the background here, tell you what I
Take your
mean.
time, take your time. It's a good idea.
Okay. Quantum symmetries, what I mean by quantum graphs, there are not going to be any proofs. So I plan to occupy most of the time with this, the stuff I've underlined, and then tell you what I mean by generically and state a couple of theorems. Okay, so that's the plan. Now, first off, what this is trying to capture is this phenomenon in finite graph theory, whereby if I select a graph at random on endpoints, so I have endpoints, endpoint space.
And when you say graph, do you mean directed graph or undirected graph?
Undirected.
Undirected.
Endpoint space X. And you construct a graph simply by flipping a coin. Let's say this is one possible model. This is one possible model of how you might construct a random graph. Maybe I want to call it GNP. NP. N is the N. You see it right here. P is some probability. And for each, this is the original, I think, random graph model invented by Erdos and Rennie. For every pair of points among the N, you flip a coin with probability P on whether or not you're going to place an edge between those points. For every X, Y in X, there's an edge X, Y connected, you see no arrows, so undirected, with probability P. And now, of course, this is an extremely finite sort of system. You can't say that much about just it. But what tends to happen in this business is people make n go to infinity. And then there are myriad variations. You might keep your P constant. You might let it vary with n in all sorts of regimes. You might bound it by log n. You might bound it by all manner of things. And you study the asymptotic behavior of these graphs. What is it likely to happen with high probability as your parameter n increases? you study the number of components, you study things like what we'll get to in a minute, things like the behavior of degree sequences. So I take the degrees of random vertices among the n, and then that's one instantiation of a degree. But by degree sequences, you might mean something more sophisticated, a more complicated structure, like you take a vertex, look at all of its edges, look among its neighbors, you take the degrees of those, then look among their neighbors, you take the degrees of those, etc. So you study invariants like that and their behavior asymptotically as n grows to infinity. And there are all manner of qualitative and quantitative results about how these properties behave asymptotically. And what interests us are symmetries, of course. I even underlined the thing. So I will remind you of the result by Erdos and Rennie themselves initially in, again, myriad variance over time, endless variation. There's a whole book by Bolobash called Random Graphs. It's all about this. The result to the effect that in this very simplistic system, so I'm doing nothing to P, just leave P alone. Leave P alone. The probability that the automorphism group of your graph be trivial goes to 1. And there are also quantitative versions of this, like how quickly it goes to 1. There are all sorts of technical terms I always have to look up. I'm not going to get into that. Extremely fast, it might go to 1. It might go to 1 overwhelmingly fast. People use these uninformative terms that I don't necessarily want to unpack at the moment. And again, remember, n goes to infinity now. That's their result. And this is the sort of thing we're trying to capture, sprinkling some quantum nonsense.
Sorry, I think that there is a question, Thomas, yes?
Yes, I have a question.
Okay.
So, do you impose any condition on probability of the transition from X to X?
No.
It's arbitrary.
I'm allowing loops. I don't care about loops.
Yeah. So loops can have non-trivial probability also.
Yeah,
okay.
That's fine.
Thank you.
Yeah. Also, incidentally, I don't think this makes any particular difference to the problem. So you might forbid loops. I don't think this is going to change the substance of the stating. Other questions? Yeah, you are. I don't see the any notifications in the chat or anything. So you are going to have to tell me if there are questions.
Yeah, don't worry.
Yeah. Okay. Right. So this is the sort of thing we're trying to imitate here. One qualitative distinction you're going to see is for us this genericity. The genericity we stabilize on eventually will not require anything to do with asymptotics, because once you go quantum, your parameter spaces are already going to be continuous now. They're not going to be discrete anymore. So I don't need to go to infinity to make sense of generic. To make sense of generic, I'm going to be able to use something like a topological notion, like maybe away from a set of first category. Or I'm going to be able to use measure theoretic notions, like away from a set of measure 0, something like that. Or maybe algebraic geometric notions, even better, away from an real algebraic variety, let's say. So the bad locus, so to speak, is going to be cut out by equations, by polynomial equations. So then the rest is very large in any reasonable sense. So we're going to be able to do that. So for us, there aren't going to be any asymptotics. That's going to be one fundamental distinction between the quantum picture and the classical picture. But morally, this is the type of result we're trying to recover quantumly, so to speak. Yeah, I hope this doesn't sound too insane for a bit of motivation here. You know, it's always hard to tell what motivates people and what doesn't, but I'm trying. So any questions so far?
No.
No? Okay. Now I'm gonna get to some of the stuff you know so well, but as we said, since I have so long, I'm gonna speak slowly. I'm gonna take my time, and
Yes.
so I'm just running the clock, Piotr. You're
Yeah.
making me speak for a long time.
Yeah.
Okay. Okay. So now let's get the symmetries out of the way. These are the ones maybe everybody here is amply familiar with. I mean, compact quantum groups. But I just want to specify that I mean them in the algebraic sense. So symmetries for us are going to be compact quantum groups. But I will remind you what compact quantum groups are. So even that I'm doing. I hope nobody's terribly upset.
No.
Symmetries, let me not misspell it. You are publishing these, right? So
Yeah.
symmetries for us, compact quantum groups. Quantum groups. Instead of this mouthful, of course, we're going to do CQG, right? CQGs in the following guise. So they're regular function algebras. You think of them as CQG, right? It's not GQG.
Yes. Yeah, yeah.
That must have looked confusing. In the guise of algebras of regular functions. So this is like an algebraic variety. So a complex Hopf star algebra. This means a Hopf algebra with a star structure, meaning complex conjugate multiplication reversing as usual. Hopf star algebra, maybe O of G. So you think of it as the dual of the CQG itself, which I'm calling G. And it's going to be co-semi-simple. So its category of co-modules is going to be semi-simple. Co-semi-simple. And
you do have a Spanish condition for the antipode, that star composed with the antipode squared is identity, right?
I don't think I need that. No, or no.
Because normally when people say like Voronovich, Hofstar algebra, they mean this.
Star. I see. I thought you were telling me I want to be cats. I don't want to be cats. Yeah.
No. Star composed with S, not cats. No, of course not.
Yeah. So star composed with S is the identity. Yeah. Co-semi-simple, and also the integral. If you're co-semi-simple, you have a unique left and right integral, meaning under the convolution product, O of G star tensor, O of G star going to O of G star. There are lots of stars here. This star means the dual. This star means the convolution product. And what you do is, you know what you do. You take two functionals and you send them to F tensor G, composed with the co-multiplication. That's going to give you another function. Yeah. Under this convolution product, there is a single left and right, because of co-semi simplicity. There's a unique unital left and right invariant functional, which we're calling the Haar state. Haar state. It's invariant in the sense that if you hit it with things, those things get absorbed. For any functional. And I want it to be positive. So that's what makes us compact quantum groups and why I'm calling it a state. So H on positive elements in the usual sense of star algebras takes non-negative values. So these are the compact quantum groups. They are cast as these algebras, these function algebras.
Sorry, Alex, does this positivity imply that H is unital, that H of 1 is equal to 1?
Oh, no, I'm assuming unitality. No, I can scale it, right?
Okay.
Yeah. H of 1 is 1. If I want uniqueness, I gotta pin it down to 1. Yeah.
Because it's what really makes Cosemi simple. If you can have some very nice finite dimensional Hopf algebras, Q deformation of SLQ2, and you add root of unity, and then you have that H of 1 is 0. You still have a unique integral when you normalize it, but it's not a Haar state.
Absolutely, yeah. If you can't find one with that's unital, it's gotta send the unit to 1, right? Because otherwise you could scale it. Yeah.
We have H of 1 is equal to 0 when you have some nice Hopf algebras.
Yes.
Root of unity.
And in that case, you have separate left and right integrals, right? It's one thing to be left invariant, it's another thing to be right invariant.
Yes.
This is left invariant.
I believe so, yes.
Yeah.
Mm-hmm.
Okay, so we're not in that case, though. We're in this one. So it's all very nice, and the Peter Weil theory of representations goes right through. The representations of G are the comodules of O of G. This is how we cast that phrase in this quantum world, etc., etc. So I know you are well familiar with this. I just want to pin down the assumptions here, exactly what objects we're working with. Again, it doesn't hurt anyway, since we got the time. And now, so these guys, these G's, these CQGGs, are what's gonna implement the symmetries. So we need to think a little bit about what that means. What sorts of things does such a G like to act on? What sorts of structures? Well, it's a Hopf algebra, and the symmetries G encodes. Was there a question?
No, I was coughing.
No, I see. Okay. Just generic noise. That's okay.
Yes.
The symmetries that you can encode as G acting on things are the comodules of O of G. So G actions means O of G module, comodules, comodule. But again, I know this is trivial to you, but I do want to make a point that's going to come back and haunt us a little bit once we get to quantum graphs.
Mm-hmm.
This is going somewhere. Believe it or not, sometimes you can't. No. So what does that mean? Well, I can have things like a comodule. What are the sorts of operations that are allowable? I can have a comodule. I can have another comodule. I can tensor them. The category of comodules is monoidal. I got that. I'm allowed that. I can dualize every which way. Because I am co-semi-simple, I have left duals, I have right duals. So I can take left duals. I can take right duals. I like to use this notation for right duals.
Okay.
Left duals in the sense of monoidal category theory. Right duals. Now, because you were compact quantum groups, in fact, because we're co-semi-simple, these are isomorphic, but you got to be careful. The isomorphism is not necessarily the identity, the usual identification of one kind of dual with another kind of dual for just plain naked vector spaces. But there are isomorphisms in the category of comodules. So these are isomorphic. The category is pivotal. If you want, it's star star is isomorphic to the identity. So these are actually isomorphic. But in any event, I do have duality. So I have things like evaluation maps. This is just the ground comodule. I might do something like this actually instead of C. I might do like the monoidal unit of the category.
Okay.
I'm going to make the one sort of bold. And then we have co-evaluation morphisms. Again, here you can twist these around, but because V is isomorphic to V star, V star is isomorphic to V star on the other side, you can flip the V and the V star, but I do like to be consistent. If I'm using the notation for left duals, I do like to write down the tensor product in the correct, so to speak, order. I have those morphisms because we are working in, we have this star structure superimposed over whatever goodness the Hopf structure gets you. We also can unitarize all of these finite dimensional, we're going to specialize to finite dimensional comodules, and we can unitarize them. There's a notion of an inner product being invariant under the comodule structure. And you can equip every finite dimensional comodule with one such invariant inner product. So these are actually going to be very rich C star tensor categories. And so we also have stars, which, so if I have a morphism of comodules, I can take the star in the usual sense of Hilbert spaces. So this is a morphism, morphism, morph. Let me try again. Morphism, this looks a little better, of unitary comodules.
And unitary means preserving this special, it's like scalar product structure.
That's right, yeah. So in fact, it's not just V, right? It's an inner product that in a certain sense, that can be made precise, of course, is invariant under the comodule structure. It's an equation you got to write down in Sweedler notation. If I take F star now in the usual sense of Hilbert space star maps, adjoints, this is going to be again a comodule map because all of the inner products being, so I have one on V and I have one on W. Now this is getting a bit confusing now with all of the stars. Now star, if you're keeping count, star has meant something like 4 things distinct conceptually during this talk already. Okay, so that's quite a bit. Now, because we have all of this duality happening that has nothing to do with Hilbert spaces, it's about rigid monoidal categories. That's a purely categorical notion. This duality here is Hilbert space dependent, specific. you tend to depict this second one by a dagger. So this is what we call a dagger tensor category. So F. Daggers are sort of hard to draw. It's sort of like a long T or something. So these are dagger monoidal categories, dagger tensor categories. So you see there's all of this rich structure. You can flip maps around by duality. You can flip maps around by this dagger operation. What else can you do? Here's something you cannot do. Here's something that's problematic. You don't have anything like this in general. There's nothing like a braiding. So we don't generally have identifications. There's no canonical maps that go like this that I can preserve. So as soon as you see something involving, because this is going to come up again in just a bit when we talk about quantum graphs, as soon as you see something involving opposite structures on algebras, it makes perfect sense for me to talk about an algebra in the category of comodules, because an algebra is something equipped with a multiplication that makes sense monoidally categorically, and associativity makes sense monoidally categorically. As soon as I talk about the opposite algebra structure, I need to flip. I need to do something like this. And that's not allowed. I don't have a flip functor in my category, generally. So anything involving opposite algebra structures is problematic from the perspective of... Was there a question?
No.
Okay. Anything involving opposite algebra structures is problematic from the perspective of casting it as something G can preserve, is what I'm trying to say. Okay? There's no such. So I have comodule algebras over O of G, meaning G algebras. So algebras acted upon by G. Remember, G is nothing but O of G, but we need to dualize the language because you think of G as dual to O of G. So these are G algebras. That's an A, not an O. But given a G algebra, given one such A, there's no meaning to A op. A op doesn't make sense. Not in the generality we've placed ourselves in. Doesn't make sense. This was the point I said I was going to get to. Okay, it will come back. When you see explicit ops in our discussing graphs, quantum graphs in a bit. Every once in a while, I'm going to swat away these red notifications. You see something red on my screen? It's email notifications. I apologize for that. Should have turned them off, but now it's going to take like a textual command. I'm not going to break to do that.
Okay.
Okay. So any questions so far? It's a good place to stop because I think I want to make the jump to quantum graphs after this.
I don't see any raised hands, so you might proceed with your quantum leap.
Okay, that was very that was masterfully worked in. I bet you were sitting on that. You've been planning it, right?
Yeah.
Okay, so it looks like I've been too successfully long-winded because this is like half an hour already. Yeah.
Yeah, it's half an hour already in 10 seconds, yes.
Okay, yeah, it's amazing. It's amazing how fast it goes. I mean, for
yes.
me, I don't know about you. I don't know about
It's
you.
relativity, my friend, relativity.
Exactly, yeah. Okay, so now for quantum graphs, since we're talking about quantum symmetries of quantum graphs, let's so before I jump, I take the leap. Let's take stock of where we are. I've said nothing about generically. We're getting to that. I've said pretty much what I haven't said everything I needed to say about quantum symmetries because I haven't specified what it is we're symmetries of. Once we discuss quantum graphs, we'll connect back to the quantum groups that are supposed to be acting on them. So quantum graphs, remind you a little bit about what these are. Remind me, Piotr, is the next speaker supposed to be Andre Cornell?
Yes, exactly. Yes,
Yeah.
he's in the audience.
Right. So he told me we were speaking back to back. He asked me what I was speaking about, so we don't overlap because we have some joint work. I don't know if he's going to talk about that.
He's going to talk about quantization of discrete structures.
Well, our work is on that, but his is broader on that topic, so it might be our joint thing, or it might not be. I don't know. Quantum graphs. I asked because I noticed your seminar webpage doesn't post advance notices of who's gonna speak in the future. I don't see that.
This is why I send this announcement at the beginning of a semester with a full roster of all speakers. So
Right, yeah. So if you missed that, you're done.
yeah, that's it. Yes.
Good. So now I want to take a little bit of time to remind you what we mean by these, because these come in many guises. Yeah.
Mm-hmm.
For us, well, you want something like this. If you think back to what a graph is at its most basic level, and again, in this business, Piotr, because I know you care about this a lot, because you work with graphs a lot. So I imagine you're going to ask, you've already asked something to this effect. These are going to be symmetric. There's no directedness here, okay? So the graphs here are symmetric.
Yeah.
As relations, I mean.
Yeah.
X is connected to Y is connected to X. There's no distinction. Okay. So you think back to get my train of thought back. You think back to how you might define graphs classically, and you might define them as a symmetric binary relation at its most basic. Symmetric, if I don't want directedness. Symmetric. I messed it up. Symmetric binary relation on a set of vertices. Now, the way we're going to normalize these quantum graphs for the purpose of this talk, not only, Tomek, do I allow loops, but I'm going to have all of the loops. So you can just get them out of the way. We're going to have all loops by default, okay? So loops you can ignore now, not because we don't have them, but because we have them all. So just don't worry about it.
Okay, so you can reformulate it by saying that this relation is not only symmetric, but also reflexive, yes?
Absolutely, absolutely. Exactly, yes. So why don't I just say that? I was going to write with loops, which was going to be stupid. Why don't I just say what was just suggested? Symmetric, reflexive. This is one variant of what you might mean by graph. And it's what's going to quantize just for the purpose of this talk. Yeah. Yes. So this is what we're trying to imitate. Now, there are quantum relations, maybe, see, what I want to do here in this review portion of what we mean by quantum graphs is I want to remind you of several notions of them. As I sink into my chair, you might start to see just the upper half of my face in the little, I hope that's fine. It's not like it matters anyway, yeah. I was going to remind you of several guises in which we quantize graphs, and one of them may be our entry point to that discussion of the zoo of quantum graphs, all more or less mutually equivalent, is going to be through this notion of quantum relation due to Nick Weaver and also Greg Kuperberg. They explored it together in the context of von Neumann algebras thought of as quantum sets. So you impose quantum relations in the sense of binary, that's understood in the theory. You impose relations between them. So I give you two von Neumann algebras. A relation is something that connects the two together. So we're going to start with quantum relations in the sense of Weaver. So classical relations are going to become quantum relations, QTM for quantum, in the sense of Weaver, in the sense of Nick Weaver, which I'm going to remind you of. I will recall what these were, just briefly.
So I can tell you that Andres' talk is going to be based on some joint work with Nick Weaver, I suppose.
Okay. These are as follows. So you start with two von Neumann algebras. We're going to be finite dimensional all of the time, but for these guys, you need not be. You can develop the theory in that generality. So these are W star algebras. That's shorter than von Neumann, right? I guess VNA is short enough. And a binary relation between them, or from one to the other, binary relation.
Sorry, just a quick question for you. W star algebra is abstract, or is it already embedded in B of H on some Hilbert space?
Start with it abstractly. I'm going to embed it in a second. And then I will say something about the dependence on the embedding. Okay,
so W star means C star with pre-dual, yes?
That's right, yeah.
Okay.
Binary, I'm parenthesizing binary because you take it for granted from now on. We're not going to discuss any other kind of relation in this quantum setup. Binary relation between N and M. Oops. I'm going to draw it as an arrow, but it's not a map, right? It means the following. So colon here. You embed N and M into B of H and B of K. Actually, I think I like L of H, if you don't mind. So I'm going to do that. So these are Hilbert spaces. L means bounded operators. And the binary relation means W star closed, weak star closed. I'm just going to say W star. W star subspace. From H to K, in the space of operators from H to K is what I meant. Invariant under left and right multiplication by the commutants of M and N. So let's see, if I'm going N and M live in H and K respectively, so I'm going to need to multiply on the left by M prime commutant, and on the right by N prime. You precompose with elements from the commutant of N. And it can be shown that the notion is intrinsic, meaning if I give you another fixed pair of embeddings, there's a correspondence, a bijective correspondence between relations involving H and K and relations involving H prime and K prime, the other embeddings. What's going on here is that if you choose, let's say, bigger embeddings, think of this intuitively, M prime and N prime also increase. So the imposition that your space be invariant under multiplication becomes stronger, so the space becomes appropriately small. It gets cut back down to size. So the size of the space involved doesn't increase. Yeah, that's the intuition here.
Okay, but is this direction right, or maybe shouldn't be the other way around? If you take something which acts from H to K, you would like to multiply it on the left by something which goes from K to K, yes?
Yes.
Okay, K is a subset of okay, M is embedded in L of K. Okay, it's
all
fine.
right here. Yeah.
Yeah.
I specifically took a minute to think about that, right? Other questions?
Usually H is before K and M is before N, so usually
I absolutely messed up the alphabet, but you do have it in front of you, right?
Yeah. Okay. This is why I was confused. Okay.
I am not prosecuting the alphabetic order. We're all on the same page on this. That's been established for some thousands of years.
Excuse me.
Yeah.
Excuse me. May I ask a question? So,
yes.
Go ahead.
so this
But show yourself.
this space L from H to K is a bimodule over M prime and N prime. If you write this in this way, are you using some star somewhere, or because this opposite algebra doesn't make sense? I don't understand. What's the action of this tensor? What is this M prime bullet N prime? What do you mean by this?
You take things in here. These are operators, yeah?
Yeah.
And you multiply them. So if the operator belongs to your space, let me write V for my relation. If it belongs to the space, and I compose it with an X from M prime,
yeah,
and I precompose it with a Y from N prime, the resulting composition is still in V. This is what I mean. You stick the thing in here. This is juxtaposition, is just composition of operators.
Okay. So why this corresponds to this relation in the classical case? Could you explain to me?
Yeah, if you do this for L, if you unpack the
if N and M are commutative.
Yeah, that's right. So if N and M are commutative, these guys check, and you can check as an exercise that this notion specializes back exactly to the to having your V be the span of the indicator functions
Mhm.
of the elements of the relation. Yeah. If M is something like L infinity of a set X, and N is something like, and N is something like
Yes.
L infinity of another set Y, then this V will live inside L infinity of X cross Y. And it's going to be spanned by the elements of a classical relation.
Mm.
It's an exercise you got to do. Yeah.
Okay. I will do it.
Good.
Thank you.
Or even better, just read these guys' paper. Or it's a, I think it's an AMS memoir. Weaver and Cooperberg are these guys. Because they do it for you, is what I mean.
Okay.
That's better. Okay.
Yes.
Other questions?
I think we are good.
Okay. All right. Yeah. So that's what we mean by this. Now we're going to specialize to, that's what we mean by a relation. We're going to specialize to, of course, it's going to be a single M. So for us, it's going to be a single M because I want a relation on a specific set of vertices, so to speak, but it's going to be a quantum set, right? So for us, binary relation on a single quantum set, meaning von Neumann algebra, and it's going to be a matrix algebra. So this is the setup for whatever theorems I end up stating. Mn. And then is going to be fixed. N is a bit like the size of the graph. Yeah, you think of this as you think of Mn as a quantum set of size n. Quantum set of size n. But it's not going to increase. It's fixed because we have a continuous family of parameters, as you will see shortly. So we don't need asymptoticity to make sense of genericity. Yeah? That's the distinction to the earlier classical model of random graphs. Okay, all right. So we want these V's in the context of this Mn. Now you see Mn is already represented by its very nature as sitting inside an L of H. Namely, it is, oops, sorry, I keep sliding too far down. Mn is, let me try a better L of a specific Cn. As soon as you've realized it as Mn, that means you're making it act on an n-dimensional vector space with a fixed basis. That's how you realize operators as matrices. Yeah. So it's already defined like so, and its commutant is trivial. In this realization. Well, it's not this, is it? It's C. It's C is what I mean. Its commutant is just C. So invariance under this composition that we were a bit confused about is nothing at all because it's just scaling. If M prime is C and N prime is also C now, I'm just scaling. So I'm not doing anything. Let me swat away another one of these annoying notifications. So the constraint that you be invariant under commutants is nothing. And we're finite dimensional, so being weak star closed is nothing at all. Just any subspace will do. So binary relation is just a subspace of L of Cn. Relation M to M for us. For us, Mn, M is going to be Mn for the duration of the talk. Because I don't want to carry the N with me all the time. A relation is just a subspace. Let's call it S of M itself. That's it. That's what a relation is. Now, reflexivity, symmetry. I haven't said anything about how the quantum notion of relation plays with classical notions of various properties your relations might have. Symmetric, remember we wanted a symmetric relation. Symmetry, flipping things around, think about that for a second. What should it mean to flip things around? So what's the symmetric of a relation classically? If I give you a binary relation between x and y, it looks like this. It's a subset of that Cartesian product. It's symmetric. We sometimes call it its opposite or whatever notation you prefer, notation and language. It's something, it is something in y cross x. I think I'm covering up my camera and that lowers the brightness of my screen. I apologize. That's happened twice.
For us, it's perfectly bright. We have no problem.
Okay. The opposite relation is exactly what you think it is. You take all of the elements of R and flip them around. So this is exactly yx ranging over the xy in R. So this is how you flip things around. Now, you have to do something like that if you want to define the symmetric of a relation quantumly. It should be something going from M to N. So it should be something going from K to H. Now, there's a natural thing you can do if you want to take operators from H to K and turn them into operators from K to H. You have operators on Hilbert spaces, you take adjoints, right? So that is what symmetry is. So was a comment, question?
Yeah, sorry. I mean, I have a slight cold, so every now and then I have to clear my throat. So
Okay. Symmetric then simply means S is equal to its adjoint. This is what all of that verbiage boils down to. This is how you say symmetric in this quantum context. And I hope the preceding discussion makes this look solid enough. And next, we also had reflexive. You say reflexive like this. The identity, just the unit morphism, the identity morphism, belongs to S. Now, you might know this package under a different name than we've used so far, right? A self-adjoint subspace containing the unit. We call it an operator system.
yes.
Operator system in M. In M. That's it. That's what a quantum graph is in one incarnation. We will see a couple others in a sec. But you have one of them as a full package right now. So it's a good time for questions.
So when you have a quantum graph in this sense, can you construct a quantum graph sister algebra out of it?
I don't know. There might be such constructions. I have not examined them.
Okay.
But sorry, in general, there is a construction of a sister algebra out of operator system, yes? Like an enveloping algebra.
But it's a different stuff. It's a different stuff.
There are several, of course, constructions. If I just hand you an operator system, you can think of a bunch of ways to make an operator algebra. In fact, there's a large one, large envelope. There's an injective envelope. In fact, so there's more than one even. But I don't think that's going to give you what Piotr is asking about.
Yeah.
You want something like a Leavitt path algebra or something, right?
Okay,
Yes,
so
exactly.
you are insisting on having a sister algebra, which would be a graph sister algebra, okay? And this being graph sister algebra,
I won't constrain relations. You see, this is what.
Okay, I see.
Yeah. That's how I understood his question.
Yeah.
Apparently, how it was meant.
I have a question. So why this construction is called quantum relation instead of quantum correspondence or self-correspondence?
You can call it a correspondence if you want.
Yeah, because it's not.
Tomek, show yourself, because when you have your camera is off, we don't see you.
Okay. So my point is that I doubt if this reconstructs the classical notion of a relation.
Well, I just said it does. We were talking about it earlier.
Linearized.
Yeah, yes.
It's a linear subspace, so it's generated by this relation. So it's like a correspondence rather than the relation. It's a correspondence generated by this relation.
But look, it recovers the relation in the same sense in which abelian von Neumann algebras recover the sets that they are functions on. If I think of L infinity of X, that's a von Neumann algebra. It has a linear structure, but you can extract X.
Yes.
As its set of minimal
sorry. No. It's not true. You can say that this finite dimensional von Neumann algebra is equivalent to some quantum set because you have multiplication on it. On this operator system, okay, you don't have multiplication. You cannot come back from something which is linearized to something which is set theoretical without multiplication.
Right. Okay. So I understand that point. But I would argue that you can compose with M and N, no? You can compose.
Yeah. Not a problem. It's not a problem.
Right.
But to recover the classical relation from its linearization, you must have some kind of multiplication or co-multiplication, some kind of diagonal structure.
No, just a second. If I give you an element in X cross Y that looks like this, yeah, I can extract it from L infinity of X cross Y by multiplying on one side with the characteristic function of X, which is something from M, and I can multiply. Right. So you can extract things if I give you M and N.
Yes, but multiplied by some number.
Right. That's fine. But
so
you have the things.
So you cannot come back to set theory. Everything is a linear combination.
Well, you're not going to get a projection. That much is true. You're not going to get a projection on the XY, but you are going to get 1 point worth of information. That point corresponds to a one-dimensional space.
Yeah, but
the same way in which you think
there
about
are infinite. Yeah. But the problem is that this space is not identified canonically with the field. There is no a basis in this one-dimensional space. So you have everything is unique up to multiplying by a number. So you cannot come back to the set theory from its linearization in this way.
But the set of lines you obtained in this way is exactly in bijection with the set of points. For every point, you get a line. Don't identify it with the field if you don't want to. Don't pick a one. It's still one line. If I have a set of lines, one for each point, that's a bijection. I've extracted a set. Yeah?
I doubt if it's possible. Projectivization doesn't help.
I'm not talking about projectivization.
You are talking about lines.
Right.
Look, my suggestion was to abandon this language of relations and speak about correspondences, which is perfect.
Look, here's what I promise you. That is not going to happen because this has been nailed down for some 20 years now or over.
Okay.
So that much definitely we're not getting done.
Okay.
But I don't even know how you do this. Maybe you can file a petition or something. Change.org. You go to change.org and file a petition.
One executive order and it's done.
All in the United States.
Yeah, he's in California.
Yeah, here.
Oh,
Yeah.
yes. That's...
Other comments, concerns about the language?
No, we can charge ahead.
Okay. All right. So we got a space there. There's also a realization of the same space, the same amount of information. The same amount of information can also be captured. So one thing, we have operator systems. This is one version of quantum graphs in the context of this talk. Q graph equals operator system. In Mn. These are in bijection with projections in the usual sense of star algebra theory. Projection, let's be consistent. I was doing singulars, right? Projection in. Now, here's where we're at. Remember those problematic ops? Projections here. The op matters, right? It's if I drop the op, that's a different C-star algebra. I mean, if you start with a projection in one, you're not going to get a projection in the other if you drop the op. Okay, you got to be careful about this stuff. It's not redundant. How do you effect this identification of operator systems with projections? Well, you do the following. Mn tensor Mn op acts on the left on Mn. So it's isomorphic to the endomorphism space, just as vector spaces, of Mn by making a tensor M tensor N. These are not von Neumann algebras. Let's pick different letters, okay? Gonna get confusing. S tensor T. You send S tensor T with S composed with blank composed with T. It's as before when we were acting both on the left and the right. Yeah, you recall? So the empty circles are compositions. The filled circle is where the argument goes. This is how you act on Mn. You stick something from Mn in here, you compose, that gives you something else from Mn. This is a left module structure on Mn. And in fact, by dimension counting, it's an identification. So you can identify Mn with Mn up like so. Sorry, you identify Mn tensor Mn up with the endomorphism space of Mn, and now you take your projection PV to be such that, so it's the unique projection by definition. This is how you, sorry, I didn't mean PV, I meant PS. S is our relation. PS, you take it to be the unique projection with the kernel, sorry, the annihilator in Mn tensor Mn up of your operator system being the left ideal generated by 1 minus the projection. I'm sorry, it looks a bit complicated. Mn tensor Mn up, that's your algebra. And I want its left ideal generated by 1 minus this projection. The 1 minus is there only to make PS correspond to S covariantly, so to speak. When S grows, PS grows. Because its annihilator shrinks, so 1 minus PS shrinks, so PS grows. Okay? There we go. Does this make sense as a definition? I want to stop for questions, for clarification.
It's unique projection with.
So you act on Mn with this algebra, and some of those operators are going to annihilate your space S, and it can be shown that that ideal is generated by a projection. You call that projection 1 minus PS.
Yeah, fine.
Yeah. So that's how this goes. And this is a back and forth. It's the same. I do mean equal here. You know, identification. It's bijective identification. If I give you PS, you can extract S and vice versa. So these are two possible incarnations of a quantum graph. And I do want to speak about a third one briefly. So Q graphs can also be encoded. Q graphs in the same sense. Q graphs can also be encoded. This is again something you will have heard much about in all of these talks. You got folks talking about quantum graphs all the time, I'm sure. As their respective quantum adjacency matrices. Quantum adjacency matrices. Now, these are going to be completely positive operators, CP maps. From Mn to itself. It's a C-star algebra, Mn, so you can talk about completely positive maps, satisfying certain tensor theoretic constraints. I'm not going to unpack that. I don't have that long anyway, right?
You have 20 minutes.
Right. CP maps satisfying certain conditions. Certain conditions. I am just going to tell you how to produce the corresponding CP map from the space, from the from the operator system S. So the quantum adjacency matrix, the quantum adjacency matrix AS, A for adjacency, and also decorated by the S, so you know it corresponds to S. You make it like this. So I want a CP map from Mn to Mn. You take your S, you pick an orthonormal basis for it with respect to the Hilbert-Schmidt norm. Let me write it like this. It's a basis, so it's a whole suite of things. Be an orthonormal, an ON orthonormal. Not ordinal numbers. An orthonormal basis for S in the Hilbert-Schmidt inner product. Just to fix ideas here, it looks like this. By definition, trace, I'm normalizing it. You don't have to. You got to scale some things afterwards if you normalize. Trace of x star y. I like to be linear in the second variable when I do these inner products. I think that's the physicist's notation, even though I'm not one.
Mhm. Yeah, but it's a good one.
Yeah. So you take your ON basis and A up to some scaling that I can never remember. You might have to scale by N. You might have to scale by N squared. So let's just not bother with this. An appropriate scalar up to scale ing is going to be this map, completely positive map, yeah? Sum of xi bullet xi star. That, so you multiply. The bullet is where the variable goes. That's your CP map. All right. AAS. By definition, this is AS. So we have these three pictures of quantum graphs. Two graphs. To again take stock. Operator systems. S in Mn. It's one. Variant. The same data can be packaged as a projection P in Mn tensor Mn op. And the same data can be packaged as a quantum adjacency matrix. Let's drop the vowels. Pretend they're optional, like they are in some alphabets. Quantum adjacency matrix A, which is a CP map from Mn to Mn. You can make the jump from here to here directly. See, I took S as my preferred object to work with, and I passed from S to P and from S to A also. So we looked at these arrows. Well, I guess one direction of each. We looked at these connections. You can do this directly. You see, A is an operator on Mn, so it lives in Mn, in end of Mn. So A belongs to end of Mn in particular, because just look at it. It's a map from Mn to Mn. We also have an identification of Mn tensor Mn up with end Mn. Now, these are not the same end Mn. The identifications are different. The A is not the P. A is not a projection. It's not idempotent in general. Just look at its shape. There's no reason why it would be idempotent, yeah? What happens is you have two ways to think of end Mn. One is like this, as on the left here, Mn tensor Mn up. Another is as Mn tensor Mn by making X tensor Y operate on some other matrix by X times normalized trace YT. Yeah, that's a different way of identifying Mn, tensor Mn, a tensor product of two copies of Mn with the endomorphism space of
Sorry, so is it like taking, in fact, a pre-dual to Mn on the second copy of this tensor product?
That's right, yes, yes.
Mm.
So A is thought of as an endomorphism of Mn in this fashion via this identification. Yeah, so it's two pictures of it's a dual picture aspect of end Mn. So using these two identifications of end Mn, you can switch back and forth between P and A. You can get P directly from A and vice versa. I'll let you unpack that. In any event, these are the three ways you could think, but there might be others. The three ways relevant to this talk in which you can think of as the three ways in which you can frame a quantum graph. It's better put that way. Okay, so now, which of these afford us good notions of quantum symmetry? Well, what should I mean by quantum symmetry? First of all, I'm going to start, whatever you mean by symmetries of a graph, those symmetries of a graph are going to certainly leave invariant the underlying space of vertices of the graph. So at the very least, I need to make Mn. So CQG acting on a quantum graph. At the very least, it should act on the set of vertices, so to speak, which is Mn itself. So Mn is going to be itself a comodule, an OG, O of G, is an O of G comodule star algebra. So it's the usual notion of a compact quantum group acting on a C-star algebra in the sense of Podlech, right? So Podlech style action. It's a G algebra in Podlech's sense. I think he introduced these first. I think. Yeah. Okay, so at least that. And now I got to worry about preserving this additional structure superimposed on the set of vertices. Preserving the S just means preserving the S, doesn't it? S is a subspace. I can simply ask that my Hopf algebra coact in such a fashion as to leave S invariant as a subcomodule. So can ask that S be an OG subcomodule. So we have the quantum automorphism group. There's a universal G that does this. We have the quantum automorphism group, count, I'm going to spell it, of S. The universal CQG.
Is it clear that it exists?
Oh, yeah, absolutely. Because you already have the universal one acting on Mn. Oh, I want to preserve the trace too, right? There's a trace.
Oh, yes. Now I'm happy. Now I'm happy. Yes.
Yeah. Sorry about that. Yeah. I mean, people construct quantum graphs on non-tracial C-star algebras. You need a trace as well. Yeah. So the trace is always in the picture. You saw it everywhere, right? There it is. Trace is always thought of as a preserve. The universal CQGG acting in this fashion. I'm simply going to write acting in this fashion. So that's one down, right? We were looking at these three incarnations of a quantum graph and assessing them for the possibility of defining a good notion of quantum symmetry. I think I got that out grammatically correctly, which is
Alex, you have a question from Ludwig.
Let's go.
Alex, can you hear me?
Yeah.
Yeah, we can hear you. Yes.
Ciao, Alex. So you said trace appears everywhere, but I didn't see trace before so far, or maybe I just missed it.
It was here. And it was here. And
here.
by everywhere, I guess I meant these two. It's enough.
Okay.
I've used it already, crucially enough, right?
Okay.
Yeah.
Okay. Thanks.
That's what I meant.
Maybe I can also take this opportunity in this moment. You said these are adjacent symmetries, so they have some special properties, yeah, because classification of completely positive is not known even for, I think, higher than n than 4, no?
Yeah.
So the classification of some class, particular class of completely positive maps, right?
Yes, but you express those properties as equations. It's something like you apply the multiplication. Sorry, you apply the adjoint of the multiplication with respect to Hilbert-Schmidt norms, and then you apply A tensor A, and then you apply M, and that should equal something. So the properties look like that. They're equations of that type.
Okay.
That correspond to the properties S has, because S isn't just a naked space. It has self-adjointness and unitality. Yeah. There are corresponding properties for A.
Okay. Okay, thanks.
Mm-hmm. Other questions?
No, we're good.
Okay. All right. So that's one version of what you might mean by the quantum automorphism group of a quantum graph. So I was going to say we have this one done. This one I'm not going to bother with because there's this op here which doesn't play well with quantum group actions. Remember, I was making a big deal out of this at the beginning. So this is a callback to that. This we're going to leave alone. We're not going to act on these guys directly. So set that aside. But since this involves no opposition in the sense of opposite structures, I have Mn as a comodule over OG, and I can ask for the quantum subgroup of the universal G acting on Mn that respects this A as a comodule map. So that's another possible notion of a quantum automorphism group. So I'm going to write count of A to be the universal CQG G acting on Mn trace preservingly. Remember, we're preserving the trace. Trace compatible, TR compatible, such that A is a comodule endomorphism. Yeah, that's another competing notion of a quantum automorphism group of a graph. Depending on how I want to view the graph, do I view it as an adjacency matrix or do I view it as an operator system? I know the information is the same. And it would be terrific if these were isomorphic. It's very easy to produce examples where they're not. They have to be genuinely quantum. They cannot be classical, but they can be abelian quantum. So you can do gradings by groups, gradings by non-abelian groups.
Ah, okay.
Yeah.
Mm-hmm.
So they're not the same. They are related very nicely. It turns out there's a star that happens at some point. So count of A, S, count of A corresponding to an operator system is identifiable with count, unless I'm forgetting some conditions. We might have some. This is one of the theorems in our paper that I'm talking about. By the way, it's joined with Mateusz Wasilewski and Piotr Sotan.
Mm-hmm.
Count of S conjugate. You have to pass to the conjugate operator system, complex conjugation. Complex operator systems are invariant under star, which is a conjugate transpose. They're not necessarily invariant under transposition. That's a different, yeah?
Yeah.
This is still an operator system, but it's in a different MN, so to speak. Yeah, so that's how these are related. And in any event, the main rigidity theorem, and I'm going to end in like exactly my 3-minute stretch here.
Yeah.
So this is one of the results. I've already stated the theorem in our paper.
Mm-hmm.
With some computations having to do with Choi matrices and so on. You can go check that. I was puzzling over it a bit. There might be some mistakes. Whatever. Whatever. We have an argument, is what I'm saying. It's on archive. And the rigidity question that started out motivating this thing, not that many generically, this thing. A statement that says this, a statement that says what I am furiously underlining now is what I have to tell you for the talk to be complete. It says the following. The space of S of given dimension D at least I want to be at least 3 and I want to be at most n squared minus 2 with count of AS not trivial is contained in, well, it's contained in the zero locus of a polynomial. The zero locus of a polynomial. On the space parameterizing these S's. It's something like a Grossmanian. So you take all self-adjoint spaces of fixed dimension, right? That's a bit like a Grossmanian, which also contain the units. So it's a variant of the Grossmanian. On the relevant Grossmanian is all I'm going to write. Relevant Grossmanian. That's a real algebraic variety. You cut out some polynomials, zero loci, and what's left is the good set that has no quantum symmetries. Relevant Grossmanian. Grossmanian. Two S's, two N's. That's the second theorem I wanted to state, and I'm a minute over time. We are done.
Okay, thank you very much for, as usual, very exciting talk. Thank you, Alex.
Thank you.
Thank you.
Okay, perfect timing. You extended your talk only by 90 seconds, which is, very...
And I wasn't early, which I think you're happy about.
Yeah, this is wonderful. Okay, guys, any further questions? Tomek, Adam, you guys.
Yes.
Yes.
Okay, Łukasz, wait, Adam. Łukasz has a question.
My question is regarding infinity, because all of the definitions that appeared when it comes to quantum graphs regard, well, an analog of a random graph of size n. While I wanted to ask, what about the quantum analog of graphs that have countably many vertices? And I'm asking it mostly because of the fact what happens in classical case, i.e. that almost all random graphs on countably many vertices are isomorphic with the Rado graph, which is highly symmetrical, while the result here for the quantum graphs of finite size say that, yeah, these are not highly symmetrical. And I was wondering whether or not, first of all, there is an intuition how the graphs on infinite number of vertices should be defined, and whether or not this break of losing a lot of symmetry while going to the quantum case will also appear.
Well, one version of how you might define them is you just imitate the relation business again. Symmetry of a relation and unitality makes perfect sense regardless of von Neumann algebras. So you can impose, or you can define perfectly fine a reflexive symmetric relation between any two von Neumann algebras. They can be infinite dimensional. Nothing stopping you. From the perspective of the symmetry of the resulting quantum graphs, I don't know that anything has been done on that count. So I have no idea if there's anything like the Rado graph or anything like that. I know nothing about it. But defining a graph should be completely unproblematic.
Yeah.
Okay.
Okay, Tomek?
So first, maybe one comment about the last question. The problem is that you can grow these sets, growing this n, the number of these vertices, but to extend symmetries, you have to extend somehow these symmetries from smaller set to the bigger set.
Absolutely, yeah.
And
Contact quantum groups are hard to make them act on big things.
Yeah. So classically, for instance, as groups of permutations, you can embed these groups one into a bigger one, another one. But here in this description, you don't have this canonical embedding. So relating the symmetricity of this asymptotic object and symmetricity of these finite approximations is not even well defined. There's no comparison between these two things in general. So this is one comment. Could you come back to the slide with this triangle of equivalences? Yes, this. So this relation between A and P. Could you show the line below? The line, yes. So this identification of Mn tensor Mn with endomorphisms of Mn. So this is not it's not an algebra map.
Right.
Yeah. So this is something which goes through in fact through dualization, because they are using the fact that this Hilbert-Schmidt
Yes.
scalar product is yeah. So in fact you are speaking about the predual of this algebra.
Sure.
This was my comment, Tomasz.
Yes. I remember your comment. You okay? You were too quick. I wanted to mention your comment also. Yeah.
I'm honored.
Okay, and I have another question. This is a question about this comparison between the classical situation and this quantum one. So in the classical situation, this classical set it corresponds to a product of copies of the field of C.
Mm-hmm.
Okay, it's an algebra. Now we are taking, as a quantum model, you are taking these matrices, n by n matrices. Okay, which means that you allow some, how to say, it's something like tunneling through these off-diagonal terms of these matrices between these diagonal entries.
So, Tomasz, you mean the fact that Mn is Morita equivalent to a point?
No. Maybe it's related somehow to this problem.
Was there a question for me?
Yeah. So the question is how could you relate this classical story with this quantized one if from the beginning your objects are different? Even on the level of vertices, your algebra parametrizing vertices,
yes,
is the full matrix algebra. It's not this algebra of diagonal entries.
Right. It's all that's happening, Tomek,
Yeah.
is the usual. It's the usual ethos, if you want, of thinking of non-commutative algebras as quantum spaces. People have been doing this for decades. This is not something I just invented now for this talk. And one such quantum space is Mn. Why? Simply because it's a non-commutative C-star algebra. Nothing else.
Okay.
Yeah, that's all that's happening.
Yeah. I know that people are speaking different things for many decades. And
right.
So I'm not going to raise
Kohn
petitions.
Kohn wrote a big book about it. This is I just came up with for today, right?
Yeah, but this subject is full of misguiding principles and
Tomasz, maybe it is related to my comment about this Morita equivalence, since if you take just a diagonal matrices, this is identified very naturally with C to the power n, and this is exactly the space of classical n points. And for the bunch of points, of
But they are not
cardinality
classical
n.
points of matrix algebra because
Yes, but now taking matrices, probably some people would argue that Mn of C is still 1 point space, but viewed from the point of view of non-commutative geometry, since it is Morita equivalent to point. Yes, so I don't know how this relates to your I don't know, objections or remarks maybe, but maybe it is related.
yes, somehow it is, of
I
course.
don't think we now here are going to resolve much because we're getting into the discussions of the philosophy of quantum theory. There's any number of ways you can think of this as sellable. For instance, you can think of, as was just being said, you can think of Mn, if you want, as one classical point, because there's that Morita thing, with some quantum spin information attached to it. Yeah, so there's some extra quantum fuzz, so to speak, but the classical portion is a singleton. You can do that if you want, but we're not going to resolve it here now. The only point mathematically is it's a non-commutative C-star algebra, and we've been calling these quantum spaces for some amount of time now.
Okay. So my only objection is that this doesn't reproduce this classical situation.
Fine.
It modifies.
As I said during the talk, you got to take it up with someone else.
Yeah.
Yeah. Okay.
Okay, Adam.
Yes, I still have one quick question. If you could go back to the end of your talk. And my question is, what is special about n squared minus 2?
Oh, it's only this. This is a very simple matter. Remember, S needs to be to contain the identity. So, in fact, I want to tell you about both bounds, right? 3 and n squared minus 2. If I preserve, if I'm two-dimensional, that means I contain the identity and one other operator. And that operator is gonna have a large commutant. So I am gonna get a big even classical automorphism group if I'm dimension 2. Similarly, if I'm dimension n squared minus 1, my orthogonal complement is spanned by a single operator.
Okay.
Yeah, that's it. That's all that's happening. So this is the only reasonable range. You can't extend the range reasonably and still expect trivial automorphism groups.
Okay.
That's
so
all.
A very simple explanation. Okay, thank you. Very clear.
Okay, let's wrap it up. Anybody else? Ludwig, Jacek, Andrzej, BJ?
Well, thank you. Thank you very much. It was very nice. Thanks.
Yeah. Thank you all. This was very engaging. Lots of questions.
Let us talk, Alex, again for an exciting talk. Thank you so much. Thank you.
Thank you all.
Thank you.
Yeah. Bye.
Please remember to save the file and send it to me.
It's the thing I do next.
Namaste. Let me stop the recording.
And I'm going to stop my share.